Hello, welcome to the video. And until now, we have seen and analyzed negative feedback system. And now let's start building up blockwise our opamp, and let's develop our opamp and let's analyze it. So let's deep dive and let's get started. So we know that we have our negative feedback amplifier implementation. So sorry, what this word? This is not integration. This is implementation. Okay, so we have our negative feedback loop, and we knew that we have two inputs, or let's say a positive node and a negative node to our input, and we need something which can integrate our input and give it as an output, and the same output will give us an feedback, which will be again giving us the voltage error over here, which will be again integrated. And this is how our feedback works. And we have discussed this in detail in our previous videos. So the one active element, which can provide us this same functionality is our op-amp, which has two terminals, and we can give input at its terminal, and we can uh, take the difference, and it can integrate the difference and give it as output. So basically it will be having its unity gain bandwidth, which is omega u, and by that factor it will integrate the difference voltage of between its two nodes. And this is basically what we want, and this is what we are going to design. So now our out of basic elements, resistor, conductor, and resistor, inductor, and capacitor, we have inductor and capacitor, which have the property of integration, or basically those are the two elements which have the capability of integrating. So let's talk about in generality or in reality. In practice, it is very hard and it's very costly, and it takes so much space as the inductor is very much bulky, and it is not efficient to make an integrator out of an inductor, whereas it is cost and space effective to make integrator out of a capacitor. And as we know, we are into IC design and all the things are very minute. So it is better to design an integrator using a capacitor, which can be teeny tiny instead of a bulky inductor. So our idea lies over here, and we know a capacitor integrates the current across it. And if we say that there is a voltage drop VC across the capacitor C, and the current is flowing, which is denoted by I, so we have VC equals to 1 by C times integration of I dt. So this is the property of capacitor. And solution to our implementation lies over here. So we have a voltage difference and we have active component, which is basically a MOSFET, and MOSFETs are the components which are being used in our latest technology in our semiconductor industry. So we have our MOS transistor, which is able to generate or make a flow of current, and based on the gate voltage given provided. So we have our voltage difference due to which current is generated, and when that current flows to capacitor, so we have the property of capacitor to integrate it. So when the generated current been flown to a through a capacitor, so we get our V out as an integration, and this is what something we were expecting. So this uh, transistor, or let's say MOS transistor, has its own transconductance GM, and GM times the voltage difference is the amount of current which flows when VD is applied at its gate. So our V out is integrated form of our differential voltage, and which is basically 1 by, we know that from the property of capacitor, it is 1 by C times I dt. So it is basically 1 by C times I dt, and then when the constant term Gm comes out, so basically it is Gm by C integration of Vd dt. So our condition or our requirement is satisfied. And comparing this to our main equation for our negative feedback amplifier, it turns out to be omega u is nothing but gm by c, and which is a constant term. Now we have a system which will take an input and integrate it, but when we apply a negative feedback, let's say what happens. So now let's get into a negative feedback system. So we have our difference voltage. So due to this different voltage, there is a current flow, which is Gm times Vd. And that current, now when it comes to this point, it has two options. One option is going through C, and we want our current to go through C. All of our current we want to go through C, as we want to integrate it like this. But what happens is there is also a resistive network, and especially when this R is very low, the current will prefer to flow through this network. So our idea was to make a current from Vd and then make the current go through the capacitor. But here, some amount of current also gets through the resistor network, and which is something we don't want. So here comes the idea of inserting a buffer. So what does a buffer does? So it gives the voltage at its input exactly the voltage at its output. So these two points have exactly the same voltage, as the gain of our buffer is 1, and buffer can drive a load by giving whatever the current is required by the load. So basically, we can say that if you introduce a buffer, it will isolate the resistive network and all our current will flow through C, which is basically what we wanted. And how a buffer looks, or if we go and see a buffer on its telescopic view, so it is nothing but it is again, it has its input voltage Vi, let's say, and its output voltage will basically a current produced and which is flown through its load, and we get a V out. So now this particular block is called OTA in IC design, and which is basically yeah, operational transconductance amplifier with a GM transconductance. And due to its convention of terminals, if this terminal is positive and this one is negative, the current Gm times Vd is forced out of the OTA. If it is reversed, the terminals are reversed, the current of Gm times Vd is forced into the OTA, and it is a voltage controlled current source. So before implementing the structure, let's think what possible non-idealities may arrive or we can have. So I think we cannot make a real ideal current source, because it's not possible to make a proper ideal current source with an ideal infinite output resistance. But in reality, as we know, the output resistance is finite, it's not infinite. So we have an ideal case where we expect that there is infinite resistance over here, and that's how our current source becomes ideal. But in non-ideal case or practicality, there is some resistance which is RDS or R naught, or it is a conductance of GDS in parallel with our current source, and that's why we can denote it with our OTA like this, or in some circuits, it is basically denoted by an arrow where GM comma R naught is mentioned. So yeah, now coming to our structure. So our structure is basically like this, where we know that, let's say there is a voltage difference which is not equals to 0. And that's why the current is flown through this R, and we are getting a V out. And at this point, we are having V naught by K voltage due to this voltage divider, we can say that V naught is at some value which is not equals to Vi times K. So the Vd is basically equals to Vi minus V naught by K, and that's how we can say that Vd times Gm R naught is equals to voltage developed across R. So at DC, capacitor is open circuit, so all the current will flow through resistor, and Vd times Gm times R naught is basically the voltage across it. So for DC value of Vi, we can say that the Vd, which is basically equals to Vi minus V naught by K, times Gm, the current, times the resistance R naught is our V naught. And from this, we can say that this is our formed equation. And when we take multiply numerator and denominator by R naught, and when we say that R naught is infinity, which is our ideal case, so we'll do a quick sanity check, and our ideal case says that R naught is infinity, and when we put R naught as infinity, it comes that V naught equals to K times Vi, and that's what our ideal gain was. So hence the sanity check is right, and we are on a right path. So now let's say V naught equals to K times 1 upon 1 plus K by Gm R naught. This is the same equation written in analog template where K is our ideal case, and this is something, a case with error due to non-ideality. So now let's look at the transfer function. So we have two cases. Ideally, we wanted the case where it looks like this, but we know that in reality, we have R naught in picture. So the transfer function will look like this, where it is Gm by Sc, and in reality, the transfer function is Gm by 1 upon R naught plus Sc. So this is basically Sc's impedance from C, and this is the parallel impedance of R naught and C. So the pole which was at origin over here, ideally, is now moved to a different frequency, which is in left hand part of our S plane. Let's discuss it further. And from this equation, we know the pole is at minus 1 upon C R naught. So let's look at S planes. The pole is at origin, whereas in reality, the pole lies at minus 1 by C R naught. And also, when the magnitude is equals to 1, we get omega u. And let's say the magnitude of our transfer function equals to 1. So by solving it, we get omega u square equals to gm square by c square minus the non-ideality term. And this value is very small. So we are all, like, we can say that we are almost sticking to the ideal case where omega equals to gm by c, which is what we discussed earlier. Omega u equals to gm by c. So yeah, coming back to our picture, let's analyze the Bode plot. And what does the Bode plot says? So the magnitude is a decreasing ramp, and at this point where 0 dB frequency lies, we have omega u equals to gm by c. But this is for ideal case, and when it comes to non-ideal case, so it will maintain a gain of gm r naught, and then when the pole arrives, which is at 1 by cr1 or 1 by cr naught, will get a decrease in slope by minus 20 dB per decade. And when the 0 dB point will arrive, we will get our omega u. And ideally, the phase is at minus pi by 2, which is due to integrator. But over here, the phase will lag by 90 degree when the pole arrives. Okay. So now let's look at the loop gain. So we have our opamp loop where we have a negative feedback, and we have omega u by s as a characteristic of our opamp. So we know that the transfer function is gm r naught divided by 1 plus SR naught, SCR naught, which we can basically say that let's look at the structure. And this for DC, we have this capacitor as open circuit, and our current will flow through R naught. So we can say that GM R naught is basically our DC gain, as our output voltage is nothing but GM R naught times Vn. So we can say, so we know omega u is Gm by C, and our pole lies at omega u by A. So from this, we can write this equation as our in our analog template, where our transfer function will look like A naught means the gain divided by 1 plus S times the pole. So this is our 1 by P. Okay, so now we have a system whose loop gain can be evaluated as below, and we have a system where the transfer function is this. We to analyze a loop gain, again we have a technique. We will ground the input voltage, we will break the loop from here, we'll break the loop from here, and we will apply a V test, and we'll see what comes in V return. So V test at this point, if we apply V test, we will get V test times the transfer function, and due to the resistive network at this point, V return will be nothing but this value divided by K. So we can say that our loop gain, by removing this minus sign, our loop gain is nothing but 1 by K times the transfer function. And when we put A not as infinity, which is our ideal case, our loop gain becomes omega u by Ks. So again, the sanity check is right, and we are on a right path. So from this, we can say that the loop gain is A naught by K divided by 1 upon S by omega u, and ideally it used to be omega u by K divided by S. So the DC loop gain will be A naught by K, and ideally it should be infinity. And the closed loop gain of our negative feedback opamp is K times 1 upon 1 plus K by Gm R naught, and ideally it should be K. So there arises a term which is called relative error. So let's take ideal gain K and non-ideal gain, which is this value, and let's take a difference between this and this. So basically the difference comes to be this value, and let's normalize this to the ideal gain we want, which is K. So when we divide it by K, so we get somewhat this function, and this is called a relative error. And we know that Gm times R naught is a very large value, and we naturally want our relative error to be very small, and we can design it to be further smaller, like 0.1% or even less than that. In reality, in industry, this is used. So we know our relative error is this, and as Gm times R naught is very high but not infinity, so we can say that 1 plus this value is nothing but 1 only, and this equation comes to be K by Gm R naught, which is basically K upon A naught. As we know, Gm R naught is nothing but A naught. So basically we can say that relative error is nothing but inverse of DC loop gain. So now to summarize, to implement an opamp as an integrator, we need VCCS, which is voltage controlled current source, and a capacitor and a buffer at the output. But the problem is the voltage current controlled current source has finite output resistance, meaning there is a steady state error or a DC error, which we discussed earlier. So opamp has finite DC gain and not infinite DC gain, which was the ideal case. So due to which the pole moves from the origin to minus 1 by CR naught or minus omega u by A naught. And we have finite DC loop gain A naught by K, which give a relative error of inverse of DC loop gain, which is K by A naught. So now let's take an example where we want our K to be 10. Now we know for sure that we will be getting an error, and let's say that error is 1%. So we want our K from 9.9 to 10.1, and thus the relative error comes to be 1%. So if we are talking about relative error, which is K by A naught, which is 10%, and we want our K to be 10, so the DC loop gain comes out to be 100, and thus A naught comes to be 1000. And we know A naught equals to GM by R naught, and GM by R naught is actually a very huge value, which is 1000. So it's okay. Like there is in practicality in industries, GM times R naught is somewhat 10,000, a lakh, a million. So yeah, so it's not just GM, but we also have to make sure that R naught has a really high value. So let's see what happens at very high frequency. Well, or let's just say that we know the opamp gain is A naught divided by 1 plus S times A naught by omega u, and our loop gain in negative feedback loop is A naught by K divided by 1 plus S A naught by omega u. So the red graph or the red curve denotes our loop gain, and the black curve denotes our opamp gain, and this is a Bode plot, and the phase change is same for both of it. But as we know that when we apply a Bode plot for loop gain, we arrive at unity gain bandwidth, which is omega loop, which is equals to omega u by K, and our opamp gain is basically our omega u point where the unity gain bandwidth lies. So yeah, these are some facts, and now omega loop is where the mod or the magnitude of loop gain is equals to 1, or let's say this value is equals to 1. So what does the Nyquist plot says? So it says that for stability, the area of interest is around the point minus 1 comma 0, meaning when the magnitude of loop gain becomes closer to 1, we are not in like we are interested in that point where the magnitude of loop gain becomes close to 1, and we are not interested in other larger magnitudes, and we know that P2 has to be greater than 4 times omega loop. So for solving for this condition where magnitude comes near to 1, or let's say close to 1, or let's say equals to 1, when we solve for it, so what we get is it's the omega, which is equals to omega u by K times the non-ideality, and we know omega loop for infinite DC gain ideal condition, omega was equals to omega loop, but reality is where the non-ideality lies, and this is the relative error in DC gain, which is very small, and by designing we can make it even more smaller, and we can neglect this part where omega is equals to omega u by K. We can assume this, and it is safe to assume this, that it is an ideal integrator, and we don't have to worry about finite DC gain, and it's okay to assume an ideal integrator even if we have finite loop gain or finite DC gain. So that's all for today's video, and I hope I have made those concepts clear. Thank you.